Thank you everyone for coming to the talk, and thank you, Chuchu, for the introduction. Indeed, I always feel come back home when I come back to MIT, come back to LIDS. So I think I hope everyone can just ask questions and feel free to stop me. It's okay for me not finishing my slides, but indeed I have some cool slides in the end. And if you have any questions, right, we can discuss today. Also, I'm so close. I'm happy to come back again to talk about collaborations. So the work I'm being presenting today is my most recent work. I'm personally very excited, but this is kind of new things I'm trying. I'm actually hoping to get feedback from people, especially I know many of you are probably from robotics and some other system. I want to hear your opinion about the approach I'm going to talk about today. So I accept the reputation-based controller learning. Probably many of you, especially deep learning people, have been talking about reputation theory for deep learning. And when I started, I was confused. What really representation means? Still, I don't have an answer for it. Today, you only hear my own perspective, what representation I'm going to talk about, and how we can use this representation to facilitate our control design. I will make the introduction very quick. I know for this community, we know these topics for a long time. So reinforcement learning or deep reinforcement learning have been kind of all over the place. Even the large language model, the last step of training, fine-tune the model using the reinforcement learning. A quick thing to setting up the tone is the deep learning is kind of consistent with our control feedback loop. We have an agent, we have environment, you call it a system plant. We interact with each other, you have sensing called observing state. The controller taking the action, the agent taking action, how we're going to update it based on the reward and state. But there's always one major difference when people really want to kind of separate the reinforcement learning and the control community. It will be model-free method will be mostly we call it reinforcement learning, and control will do model-based method. So I'm not going to argue which one is which. This is put this picture. I will come back to this picture later. So we see a lot of success, and as a control engineer, so always one question is, can we transfer success to the real-world physical system? And my background, I've been working on power system since I was a student. So actually I started even writing one survey paper. Can I really do the reinforcement learning for power system? What are the pros and cons? So once you look into it, we haven't really seen much the real implementation success from the deep learning or from reinforcement learning in the physical world. The challenges, this is just to name a few challenges, definitely many more challenges. So first thing is the data. So for the data, we really dive into the success. So start with the AlphaGo or the video game. The data you can keep generating using your own simulator, and it's going to be the exact what's going to happen. But for the real world, the system we care about, either is a power system, transportation, manufacturing, and robotics. Let me highlight one thing. I would say less data. What do I mean, right? When we were trying to scheduling, for example, the power system plant, how are we going to do it during the normal condition? We already had a lot of experience. People already know how to do it, right? Why we want using more advanced method to handle the real situation. In the future, climate change, and we have more electrification, what solution we're going to do? And those data is not really available. And there are many other things, like the data quality and also who own the data, a lot of issues. So computation. Computation is, I've been working on smart system, power system. And always one big difference is not really putting everything into the data center, solving all the decision variables, and tell individual device to do what action. We're going to have individual smart devices that can take care of those kind of fast changes or fast disturbances, and we have some slow scale planning, all these things coming together. It's complicated. So if I look into individual reaction, say the transportation, the power system, the immediate feedback is sensor is smaller, computation smaller, communication also is limited. So all these things are very different from how people really train the large foundation models. And last of the safety, for all the things we care about, doesn't matter which kind of physical system, it always has a physical constraint. And power system, we don't want to go to the blackout like that. Robotics, very important. Transportation, if people talk about remove the traffic signals. Once we remove the traffic signal, exactly how we're going to coordinate is, in theory, we can do it. In practice, still far away to go. And reward and cost, this is actually why in the past few years, I started working more with different collaborators from different communities, including the hospital, the biomedical device, and people from the biosensors, the real tissues. And always one question come up is, if I do the reinforcement learning, I need a kind of setting like reward function. What is really the reward function? No one actually behind me, this is the reward function, go ahead to do it. Even for large language model, like the success, because people actually figure out a way like to really rank those different choices, pick up the right reward. It's actually very difficult to really define, to quantify in many cases. And many cases, it's actually very hard to align people's interests, especially when we're talking about human in the loop and multiple human in the loop. So those are the challenges. I wouldn't say I will answer for all of them. Since I just want for those new students who hasn't really seen me before. So my group typically working on those problems like control prioritization and learning for dynamical system. The way we usually do it, very similar to like how our LIDS style. We will talk with the expert, figure out what's really the problem. I like to use optimization to guide the design. It's not like, say, the real problem fits to everything. It just guide my design. We'll figure out the cost function, figure out the constraint. We'll figure out what's really the state really evolving, what's the control action we can take, what's the objective function, what's the constraint. Constraint can have a coupling constraint, can have a local constraint. So once we roughly understand what's going on with the system, that's my objective, go ahead to talk about what's really the constraint for my control policies. There'll be computation, sensing, communication, different type of constraint. Like put into this, I would like my controller satisfy those, then I can implement them. So if I put in this picture, like I sometimes using the two layer, the bottom layer means the physical network, and the upper layer means the control action, like different kind of constraint. So if we dive into the literature, this actually fit into the large-scale control, distributed control problem, like our community working at for many decades. The very nice theoretical paper say this actually can be easily becoming an NP-hard problem. So the solution is go ahead, like it's not like stop there, okay, now this is a very difficult problem, stop working on it. No, because we have this real problem we need to really address. So we go ahead to exploit the structure of it. So I added one component compared with my previous talk, like a few years ago, added representation, which I will talk about today. Is try to figure out, is there any way to really rewrite the problem? And that probably can lead to some computation tool. I will come to talk that in a few slides. And besides that, if I'm really working on the real application has a lot of the structure and prior knowledges. It's just definitely a mess, like how exactly we're going to use the knowledges. So if I have time, like hope I can spend in just like for each application, I have a 1 or 2 slides, and you will see it's actually, like you want to say representation part I'm going to talk about, are powerful, but once you work in the real application, probably still need to change, like to really working on the specific structure. So now today's talk, as I said, I will theoretical component, I'm focusing on the representation. So what representation do I mean, and what's really the goal of it? The bigger question is this: how many of you have actually tried implement RL algorithm for your control for whatever problem you have been working on and implement it in the PyTorch, those things? How many of you? A few. What the experience? So I also tried. A few years ago, like I was trying and I'm very frustrated is I couldn't really make things work, right? From the paper, grab the GitHub code, supposed to just click the button, should work. Not really, like if I change a little bit of parameter, I couldn't. I see my former undergrad student Victor is here. I remember he was doing the senior assistant with me. Eventually he made the multi-agent work, but the single agent is still not going to work. Very strange, very frustrating. But on the other hand, we know this that people actually have some control policy going to work. I mean, is there any, like the big motivation for me to start this work is I want to kind of understand what's really going on with the RL. Is there any way we actually can take advantage of both? Because if I do the control design, the linear system, the nonlinear system use the LMI, I feel more like if I can, the problem fit into the size, I can get some solution. But the RL has a different experience. So that big motivation, let's see like what I can really use in advantage. Like taking the RL as a computation tool. Let me say that. Computation tool. Can I get in some control policies? Don't worry about the theoretical guarantee first. Like to making sure people like me, not from CS training, it will be easy for me to train a policy. So I will use the problem, the notation again. Let me dive into this notation. This is just a kind of very standard nonlinear control with stochastic noise. State. And apologize for the control community because I'm using the RL notation, called the state as S, not X, and action as A, not U. But you got my, so I'm fitting to because I'm going to mapping with RL. So it has state, well, it has state transition, has a control action, is A, and F is the state transition dynamics. And this is a noise. So this is the reward, and this is the discounting factor. The ultimate goal is to try to learn a policy. Let me focus on the fully observed case. I have measurement of the S. I want to get in the feedback policy. This can be stochastic policy. This is my goal. I want to find a policy to solve this problem. First, just a computation. Like I can just go ahead to implement to see the outcome. I will have a 3 component. First, just say I have the model. I'm actually, while studying working on this, like, yeah, I have been always try to avoid nonlinear system control because I don't know too many tools. And now, like, since a lot of application that people approach me, they know this is my problem. Like, okay, everything is nonlinear. So I want to see what the computation I can tell other people to go ahead to try. And if the work is work. So like, let's look at if I have the model, like what can we use the RL as a computation tool? And now that like the representation probably can even help me think about if I have uncertainty of the model, can I do better? Not do better, like can I figure out a better way compared with other RL method to know what really we need to learn, explore. And last one, kind of the control we care about robustness, care about safety, is the framework I'm presenting is able to add the safety and robustness component into the framework. So 3 components. Let me dive into the first one. The first one will be the probably most detailed one to tell you what is the representation. So the reason I put in the notation as S and A is I want to connect with MDP. So let's review the MDP and deep reinforcement learning. Right? Start with the time, same thing as what we usually do. Discrete time has a state, has action, state transition. Typically, MDP will using it as a state transition probability, like given the current S, current A, with the next state. State reward, same thing as before. Policy, same thing as before. Trying to find a policy to maximize the reward. It's almost the same as what I showed before, only in the way to writing the state transition is different. And RL will just bring the agent environment interact with each other. Like the method, now back to the deep RL, like I was playing with the soft actor critic. But typically for all those RL methods, whether it's a policy evaluation method, policy update methods, overall the frameworks can actually very similar to each other. So for the actor, it's figure out the parameterization of the policy and then do the policy gradient. Right? The different variation of the gradient, but most of them kind of following this type of policy gradient using the reward observation to estimate the gradient. So you don't need to really understand, like figure out the details where the policy gradient theorem comes from if it's the first time you see it. So there's the one thing is the Q function. What the Q function is, the Q is the reward to go. If I'm at current state S, action A, taking a policy pi, how good my policy is. If I know the Q function, substitute into the policy gradient theorem, estimate the gradient, and keep running. So that's what I call critic. Critic means to do the policy evaluation, and you can have a different way to do it to estimate the Q function. It's kind of interaction between the actor update and the critical evaluation, keep running it. So for people like me, like who hasn't really trained a lot of deep neural net, the first question usually like, what is the deep neural net I should try? That's always the first question I ask my students if they come to tell me I did a deep learning fitting the model. Like, what is that deep learning model you use? Did you try some other things? It matters. And a lot of choices, there's a lot of parameters. Like, so that's why sometimes people are good luck, it's work. Sometimes I figure out so many things, still not going to work. Can we have a systematical and like way to parameterize the deep neural net? I'm not going to talk about the actor. The actor is ongoing work. If you're interested, I'm happy to talk about that more. For the critic, we actually have some structure, probably can go ahead. I'm only going to talk about critic. Like the critic is to evaluate the policy. Like to people put in the, let me repeat, using the deep neural net, like given the state S, action A, how good my policy is. It's kind of big Q table. If it's continuous, you need a continuous function. So let me re-examine the Q evaluation. I hope exact people really down for the Q evaluation. Even there's so many different methods, like TD learning also you can have parameter tune. A loss method, right, this is kind of the central thing. It's a Bellman update. You can have the Bellman optimal update, or just here is given the policy, the Bellman update. Given the policy, like the V is starting with the state as prime, what's my cost to go, and mapping to the Q function. And you can put in the Q back there, you have the fixed point updating, fixed point equations. So that kind of usually is the way people go to update the Q. During the fixed point, using the Bellman update, you have different way to update the fixed point. So one big question, right? This is the kind of, I go to learn the Q, I will kind of using this kind of equation to do it. So what kind of parameterization, a function approximation, I should do for my Q function? There's a question mark. And let me put in here, like, can I use some information to help me? So there's a key fact. Let's say this is the assumption condition. If my state transition probability, again, this is based on current S, A, transition to the next state. Enjoying this decomposition, it's kind of, you say it's a linear decomposition because there's an inner product, has two feature functions. One is a phi SA, one is mu S prime. Kind of decoupled the current state action and the next state S prime. So if it has this, what's going to happen? If we have this, just go ahead and substitute into the Bellman updating, like the Q function, it will satisfy that equation. What this says is the Q function under the policy pi, doesn't matter which policy. It doesn't matter. You just kind of follow just one line of proof. The Q function will stay in the same feature map of the phi SA. And this additional component comes with the reward function. Like I said, now I'm doing the model-based approach. You know the reward, you know the function, you know the F, so that's the feature. So what this says, if I figure out a way to represent my state transition probability linearly with respect to this feature function phi SA. Phi SA can be nonlinear, anything else. Then the byproduct is rather than to figure out what the parameterization for my Q is, just stay in the same feature space. And when I go out to learn the Q update, phi SA is kept the same, don't change. Doesn't matter what your pi is. Just go out to update the W, the weight, which is least square problem. And we know least square problem, we actually definitely put in optimization. I know that's my optimal W. So this is probably the most important slides. I think most of you ask one question. This is a very nice assumption. When that happen? If you follow the reinforcement learning community, the theoretical paper, this actually in 2020, 2019, they have this linear MDP paper talking about the linear MDP can reduce sample complexity dramatically. And there's another name, you can call it a low rank MDP. Right? The rank comes from how many phi SA you need, and that's how much rank you have. So it doesn't matter how big your SA is, it's only depending on the dimension of the phi SA and the mu. So I started reading those papers, and the question always comes to my mind is, how you can assume that? Who gave you that? But where does linear structure come from? It's not for theoretical research, but what does it mean in practice? So that's the question, right? What happen? Feel free to ask me questions. Okay. Now, the one contribution, what I might talk is, indeed, this is actually helpful. How are we going to connect? So this is a little bit preliminary of the kernel, the positive definite kernel. So from the function analysis, the real analysis, what people can show is if I have a kernel, like when you think about kernel, you can think about a quadratic function. So kx, I'll cover xy, and this like the second condition, just making sure it's positive. So why I mentioned that is, let me put an example. For example, the Gaussian kernel, which is actually just a Gaussian noise distribution. And this is a positive kernel. Because if I have a positive kernel, it's kind of similar to even in the matrix case, if I have positive definite matrix, you can do decomposition. if I generate this concept to the functional space, if I have kappa xy, if it's positive definite, I have a nice decomposition. The decomposition is like, well, depending on what kind of kernel we talk about. So look at the expectation. The expectation has a psi omega and that's conjugate. But I have kxx prime, and I should figure out a way to define the inner product. And that's my feature function. And how it's connected to the control problem I talked about before. Let me stick to the Gaussian noise. If the noise is Gaussian, and f can be nonlinear, write the state transition, the state space model, in terms of the state transition probability. That's how it looks like. And then I showed like the Gaussian kernel is a positive kernel. What this means, I apply the theorem, I can write it down my state transition probability in terms of the inner product between psi f. The conclusion is, if I have a nonlinear system as for the Gaussian noise, I can write down my state transition as the inner product of the feature space. And the feature space that you're given, it's not like you don't need to learn. The f just substituting in is a psi omega FSA. The psi omega, to make it more concrete, what it's really corresponding to is a sine, cosine, sine omega, cosine I omega. It's kind of similar to those Fourier decomposition, all the things. So I got those linear representation naturally, like kind of for free because some noise. And this model can also be extended. It's not just Gaussian kernel. Gaussian kernel is just one special kernel. You have many other kernels. So the noise model, like how general I can do is depending. Like you can identify a noise model, whether you have the kernel representation, and then that is going to be the representation you're going to have. There's one caveat. The caveat is this. From the function analysis theorem, like you look at this is expectation. Rho omega. Rho omega is also another Gaussian distribution. It's an infinite dimension. I aiming for some computation tool. Like infinite feature is not going to be useful. One way I can do it is I can try to do the decomposition, like to the truncation. Like how do we get in the finite dimensional? Actually, two ways that we have been trying. One, since it's from the theorem, it's expectation through the rho omega. Naturally, we can just do the random feature selection, follow the rho omega, doing the Monte Carlo, pick that. Another more sophisticated way is that this is kernel decomposition is very similar to the matrix decomposition. Pick the top features. So we indeed did both, like the random feature, the two ideas we're talking about. Like now you actually can see the psi omega, that's the psi omega. Like what's really the feature function choice going to pick. Random feature truncation, just sample the omega I according to the distribution, and then using that as a feature. It's finite. And how many do you need? Thanks to the, before the deep learning kind of taking over all the things, in machine learning community, the kernel is a big machine learning community. Actually, a lot of work already developed by them. They know how many features do you need and what's the gap in the function space. So I had all those analysis that you can go ahead to grab for the theoretical guarantee. So this is the one method. We can do the random feature selection. If we spending more computation, we can go ahead to pick the top features. The top feature is from the Mercer theorems. Indeed, we actually can rank using the lambda I, and you can totally like put in the special features. You can rank them, and depending on your criterion, like how much you really want to close the approximation and the state transition, pick how many you want. So just another way to do it. Any questions so far? Yes.
When you do the random features,
yes.
Do you only sample them once at the beginning for all time, or do you sample them, like when you're running your control line, do you resample them?
So great question. So for the first part talk, because I assume I know the F and I also know the R, so for those things, all those feature selection can be offline, right? Like spending time, go ahead to pick, and you can notice, right, for those feature selection, it's mostly depending on the noise model, even not really too much of the function FSA. So for our implementation, we did offline. We didn't do the online. And second part of talk, I would really go ahead to talk about how to generalize this one to be finding the general PSA. And that one we're requiring like probably better to do the closed loop. Yeah, great question. Other questions? Yes.
So when we want to approximate an expectation with respect to a density function, we also can do quadrature. So why quadrature is not a...
You can do other method. This is two methods we did. And also the reason, I think for these two methods, we submitted the paper to TAC with all the theoretical guarantee, how many features you need. So like this two has a rich literature. We can really like do the performance that can bond in the arrow. Like other method is, I think is definitely open, and you will also see later, once I really talk about learning the feature, am I even not doing the one I'm doing right now, I'm doing some other way. Yeah. Thank you. Other questions? Good. So let me summarize. I said it's actually more like a framework. What does it mean? It's like I provide a function approximation. Like what's really the space I should state in? The way when can work with any kind of deep RL toolbox is like actually for our implementation, we took other people's code, swap, like just, hey, the parameterization for the queue using the one we did here. We don't need to really reinvent the wheel, or let me like have a totally different method. You need to have a like, we actually kind of can use the advantage from the existing tools. So first, let's kind of back to the question. We actually will compute those finite dimension special features. And then we parameterize the Q function according to the feature space. And the theta is the thing we need to learn. The theta, like the feature phi, once we did like the first step, we're not going to change. But how to update the theta is going to be online. Like based on how much data we have, we can keep estimating the Q. So now let's go ahead to plug in the critical update, as I didn't really touch how we're going to update actor. Actor will probably still the same thing as before, but the critic stay to this space, to this square. I can guarantee this is the best Q you're going to have. So let me show the simulation result first. So we had other fancy simulation like the OpenAI Gym, but for me, actually, I like studying with the problem and really know what's going on, the inverted pendulum. So we did inverted pendulum, and I think for the control community, right, I think the IOQR, the popular method, and the Kuhlmann operator is kind of people, oh, Kuhlmann can make the system becoming nonlinear to linear. Definitely can discuss more about our own experience on the Kuhlmann. It's not that easy that you can really change your problem from nonlinear to linear. So you can look at here. So this is our implementation. Even to just swing the inverted pendulum from down right to the upright position. The one caveat I will say, because people, when I present this simulation result, the people who are working on ILQR come talk to me like, Dina, like, I have a different experience. The iterative LQR works very nicely. So one thing break the ILQR is the noise. So if you add like additional any kind of disturbance to the dynamics, because iterative LQR based on iterative linearize, you need to really kind of have a very controlled environment. So we add in the noise model, then studying breakdown. And similar for the Kuhlmann, once you add the noise into it, performance becoming bad. But since the method I was talking about kind of really take advantage of the transition probability. So it's actually work when you have a noise. And then we did for the quadrotor. I will come to the quadrotor later. Like we actually really eventually implemented on the real quadrotor to see the performance. And this is the kind of training map. This is kind of the feature. We actually, like from the simulation, we try to play with how many features we need to have and to see how the performance change. And the first time last year when I present some preliminary result, and there's a senior control professor come to challenge me, asked me to check the old literature by our control community. I think there was 1990s. There's some competition to see who can have the lower cost on the pendle board. The pendle board is actually the double inverted pendulum because it's on the iterative system. So we benchmark with, I think the best, I think this is a paper that we found has the lowest cost. It's using the energy-based method. A lot of customization like, to make it working. So I highlight that one. You can compare, right? Especially once we add a noise, our method can show a great improvement of that. So now let me just have one slide, say the theoretical guarantee. Indeed, as a people training control, I want to know something like if I making some assumptions, what you can have. So theoretical guarantee, if I start with direct talking about analyzing the deep neural net actor, all these things from the soft actor critique is like almost impossible. So we change our actor to be the natural policy gradient and the softmax policy update. There's some details like the connection for this one with our representation. So once we change to this one, we're actually able to reanalyzing the performance of my system. There are actually like 3 arrows we need to take care of. One is the approximation arrow from the feature truncation. And second one is the statistical arrow when we do the Q evaluation. The Q evaluation, to make it computational doable, is actually getting samples. Even we already know the F, but I'm using the sample to do the least square to estimate the Q. And the last one is a policy iteration, like based on how many policy iterations, like it will getting better. So I will refer to this paper. We had a journal version, like on the ACAP. It's including all the components. You can see how the number of features and how the number of data will play a role to shape the event, the final outcome. With that, I conclude my first part of talk. Let me dive into the second component, right? The data-driven representation-based RL. Like the reason why we're doing RL, because we want to work with the system that I probably don't really have exact model. So let me put in the, once we dive into the unknown part. So any questions so far for the first part? Yes?
There was a table of the results from 1995. I didn't understand which of those you can compare to yours. Which column?
The first 2 are our method. The first 2 rows are our method. And later on, like we compare with ILQR, Koopman, and energy-based method. And energy-based method, if you dive into those literature, even pendulum, the unit pendulum, we also can find out-control literature had using the energy-based method to really, because this is one difficult, like, I use unit pendulum for my undergrad control class, but we're only talking about the final stage, and that one, the linear controller will do the work. But the difficulty if you really go ahead for the entire process. So the energy-based method is actually able to really define energy at different mode, and you go ahead using the energy to guide your control design. Good. Any other question for the first part? Now, let me continue. Right? The conclusion is, if I have really a nonlinear model, right, I can go ahead, like do the, it's not like some system I cannot do it. I mean, you can put in any kind of F, go ahead to implement the method. But now, when we don't have the F, where the feature come from? So first idea, right, is, okay, go ahead to the following the model-based idea. I will pick a class of the model, which is the F, and using the data to learn the F. Now with the F, then substitute to the representation I was talking about before. The VSA will be those psi, omega, like FSA thing. So this is one. But on the other hand, like, what's really the key thing I presented before? It's not really like the from the F to the decomposition. It's like the transition probability itself has the state transition. Now, if we look at this one, like I was also looking to like speaker come talking about the tensor decomposition. So if you look at the probability state transition here, the P, as 3 components, you guys can view as a 3-dimension tensor. I mean, if your S, A higher dimension is like bigger dimension, but it's a tensor. So what it's been doing here is decompose that's 3 input into the inner product of 2 feature function. That is the key. And that decomposition can be general. Like I don't need to start with the kernel space at the beginning. It's coming back to the mathematical study of when that will be possible. And I can start to parameterize and to force do some decomposition using, there's actually so many different ways also. Again, like machine learning, people has a lot of kind of tools we can go ahead. So that's kind of the second idea, right? Rather than to really taking the F, fit it into the function like the 2 random feature selection, the next one, I'm probably using the data directly to learn some decomposition. I'm not saying it's easy. So like I'm only provide some high-level idea. Right? One way like is this kind of the loss function. Okay, go ahead to just find the phi and the mu. Probably if you notice, if you work on diction learning, like this like looks like diction learning is definitely not convex. So I'm not claiming we have a solution to really say that we guarantee the definitely the best feature. But on the other hand, we actually deal with is a probability. space. So which you can use, like this is the MLE estimate to do it. And also the singular value decomposition, the recently also progressed on that. But I can go ahead to think, just think about as a singular value decomposition, tensor decomposition, to developing the tools. So these are kind of 3 examples. Thing is, we are still working on them. Like we had a method, had implementation, but we are still kind of slowed down to go to revisit all different things. If you ask me which one is better, I don't have an answer right now. If you're interested, definitely happy to talk about more with you. So just examples like we can use in different way from the data to learn the feature. So then I put in another more difficult question. Doesn't matter which method. If I just do the certain equivalence, that's the way you go ahead. But the difficulty is you want to do more exploration. And once we have put into this space, the decomposed space, so how can I really balance exploration and exploitation? Right? I need change, don't just do the certain equivalence. I want to keep adding some exploration. So just to give you a high-level idea, there's something we tried. So for the first method, it's actually kind of straightforward. It's if I assume in F is from a function choice, a space, I parameterize it. Every parameter has some random distribution, doing the Thompson sampling. But each time you just random draw one F, design the controller, and that random draw from Thompson sampling will bring some exploration. And second method for this one, what we can do is the key for this method, like I have the feature, use the feature to learn the Q will lead into the pi. So if my Q, I can do the upper confidence bound UCB type of algorithm. For my Q function evaluation, besides what I have before from the data, I can add additional bonus into the reward function. And for that one, to encourage exploration. So we have papers to talk about some choices, and all the choices have some theoretical reason why we're picking them. But again, like I said, I think there's a lot of room to continue, which is better, how you're going to really do the trade-off. So as I said, we did some fancy numerical simulation. I will actually do quick for this part. Every time when I look at all the IO paper, all the paper claim they're the best compared with the literature. So similar for this one, don't really getting much insight. Let me dive into more about the physical implementation that my lab was doing. So when we were doing it, we found that this now easy for me to train. So we felt encouraged to go ahead to look at real robot. So I have a small robotics lab, not as fancy as the backpack. Humanoid is the drone, like the middle one, that's from my lab. So we started looking at the drone. Can I really use in the method I had before to do it? I will see the advantage for the representation we're talking about. I'm only talking about, now when I say sim to real gap, I'm only talking about P0. Right? No matter what simulator, I will assuming some, say, transition probability or the dynamics, I will call it P0. And the real system is always going to be different. You don't know the parameter from all the things. So that's the one I'm focusing on. If I apply my method before, whatever the feature I learned from simulator, it's going to be different from the real feature I need in practice. The advantage of putting into the linear space of the non-linear, putting into linear represented to the non-linear space is this. Look at here. So recap, this is a simulator. Based on simulator, actually I can learn the feature, the decomposition, and the feature space phi naught, mu naught. And then I learn my Q, the Q function will be just using the phi naught, the feature space. The real world system is not P naught, it's P. So my phi naught, the highly possible, is not going to recover what really the P need to be. The good thing is, since SI is kind of linear represented, but okay, it's just a feature, it's additional bases. So when I go ahead to do the real world, rather than to just forget the simulator, I will just go ahead to add additional feature. So even my feature learned from simulator is not that informative, it's also fine. Just, okay, you have a feature, you kind of think about you have a space, you put in more bases, it's not going to hurt your performance. But your data will tell you how much weight you need to adjust. So this is a P, and then my Q will just concatenate, adding additional feature into it. I'm using the new data to update the omega corresponding to all those features. So how to learn the new feature efficiently? The thing I also want to highlight, like hope I can deliver the main message clearly for those slides. An advantage I mentioned, like, because the linear space representation actually really guide me what really I need to do. Let me put it here. So this is my original phi naught, right? It's going to be, you can think of those as bases. They will span to certain function space, which is probably p naught is a good approximation, but p is not. Then I go ahead, like, if it's not really that good approximation, I'm go ahead to add features. So when I'm adding features, that's kind of when we were, like, if you remember the, when we doing the linear space, adding additional bases, the better way to making all the bases be more useful is you can impose orthogonal constraint to make sure I'm using the data more efficiently to learn the thing I don't know yet. So when we're doing the implementation, the new feature, we add additional constraint to making the data more efficient to impose the orthogonal constraint on the new feature we're going to learn. And it's actually easy to impose. Just put it, okay, let me requiring the inner product between the old feature, new feature, the inner product being 0. Any questions? Good. So now you can say for the linear feature representation, there's a one nice advantage in my opinion, like is I know how to deal with this, in the high level, the linear space. I'm go ahead to put in my data into the unknown space that I don't know yet. So with this, like we implemented on the crazy fly, that's in my lab. So you can look at the gap. The way we implement is first because what we're doing crazy fly is being used for the community for more than 10 years. There's a lot of simulator available. We pick one simulator. We do the physical simulation and learn the phi naught, mu naught, especially the phi naught, and put in the initial policy, and you implement the initial policy. It's not going to work typically, and you're getting more data. Like even not work, you're getting more data. So using the new data to update the feature space. And once I have the new space, and then go ahead to update my Q function, update my policy, implement, get new data, repeat the process. And each time, like it's kind of for this sim tutorial, is once new data come in, I'm going to improve my knowledge of the new feature, and which going to plug in to the IO method later. Hope it's clear. Good. Now, this is the implementation we did. So this is the initial. We just implement the policy from the simulator, right? Just hovering, stabilizing, coming back. And then we did a one, like, okay, I learned the phi naught, using a phi naught to update my Q to getting a new pi. And to see how that's doing. It's doing better because I'm adjusting my weight, but not that ideal. And then we did, I think, 10 iterations between, I said I have the loop to update my feature. So this is eventually the performance of it. And one thing I want to highlight, which I'm proud of the student, is also the algorithm. For the demo, it only took us, once we have all those algorithms, all the things ready, like we know what we're doing, just about a week, we're able to have in this demo. Right? That's kind of one of the reasons, like I'm feeling like, let's work on the algorithm, feeling understanding what's really going on, and before we do any kind of real physical demo. But the student definitely, he's very skilled. Like, I'm not able to make a demo successful within a week. There's a lot of things going on. So, and then I like, can you try some other task? So we did a trajectory check-in, is try to draw the 8, the different algorithms. It's actually harder to see. We also kind of optimizing like the comparison and the built-in control, which are pretty good because kind of they already trained, like do the reference tracking, do very well. So now you actually can look, this is the trajectory problem. So from the cost function, I think back to the motivation, like actually sometimes define the cost function of the thing is kind of very open-ended, right, depending on how you're going to define it. But now we look at the trajectory itself. The 8, I would say, compared with the built-in controller, but the built-in controller, even the cost number looks small, but I would say that 8 is not really that like 8 compared with the first, like the 8 from our own algorithm. I probably like that. I don't have work to show it, and sometimes people say I have trained the policy, optimized my reward, but probably that policy is probably not really that meaningful, depending on how you define your reward function. Right? This is do the tracking, and that's the 8 come from the built-in controller. So now I have only a few minutes, just quickly to show the method is able to add the robustness and safety with, like, come back to the framework very quick to show it. The safety, I showed one thing about the feature space, focus on the phi. I didn't touch the mu. The mu is actually also useful. So like for the robust safe, I put in one problem will be robust thing, like the robust set is your P or R is like you have a perturbation set, and safe constraint, a different way to model safe constraint. So one like more straightforward way to plug in the representation that I talked about is to do the occupancy measure safety. I think Chuchu had a paper using this type of safety constraint. There's a reason is the state occupancy, if I use this feature, it's kind of have the story I talked about before. I didn't, like the phi kind of missed in my, the mu, but once we add in the safety constraint, the safety, the d t pi is a state visiting distribution. Like that's the probability that you visit the state S on the policy pi. To do the, like we put in the constraint, like say, okay, I want the distribution closer to a target distribution, or you can add a hard constraint on the distribution, you can shape how the distribution look like. So if you're writing down the state visit distribution, it's actually linearly represented state in this space, the additional feature I have already talked about. And what it means, if I do the RL method, I will apply the data to learn the D and stay in the same feature, do the square. So I'll skip this, give the interest of time. But you can see like it's kind of you plug in the method people have. I think the primary dual is Chuchu's algorithm, like the inner loop. And on top of it, you can add the feature learning. And the robustness is actually harder. So I don't have time to talk about robustness. I even don't want to spend too much time. The robustness is, if I just follow standard literature for the robustness, adding the perturbation. And then the perturbation for this way, adding the perturbation on the phi, adding perturbation on the mu. This actually will lead to the problem is like almost impossible to solve because there are too many perturb at every SA. If I have a continuous control problem, you're going to have an infinite choice of perturbation. So I'm not going to show how we're going to do it. Is the way when we're doing the robustness, ensure robustness, to dive into the algorithm itself. When I learn the Q, what exactly the Q has, like how the feature ring is showing up, to change my perturbation set to be the perturbation that's being used in the algorithm. Like can we say effective perturbation on the robust policy evaluation. Rather than perturb on all the SA, we have kind of one aggregated perturbation. And this is the more conservative, but actually more robust. So again, I don't have time to show it, just show some simulation result. So this is safety for the inverted pendulum. We kind of create something called a safety stat and put in the distribution more on the safe stat, and to see whether the algorithm, once it's reached the safety stat, it will just stay there, not coming back. It's like roughly, like this is like very recent work, we're still working on it. And the robustness one, we already submitted the paper, so you can look at here. We do the inverted pendulum. For the nominal plant is putting the mass 1.0. We train the policy, and then we test using different mass and to see how it's going to work. For the robust MDP that I was showing before, and you look at once the mass increase, the robust version will do better. So with that, I think I conclude my talk. I kind of focus on the representation, right, to think how we can design a computation tool for the nonlinear stochastic control. So right now, my group is trying to develop in the toolbox, so people can just probably write down your F function, and hopefully you can just click the button and you've got some control policy to start with. So there's a lot of like excitement. I hope like in a few months I will have those things available for everyone to try. Right now, if you tell me the F, my student can give you a controller you can start with. So I have a few minutes. Just want to show this one. As I mentioned, because I really want to talk about some application we did, which is different from just doing the representation. So this is the one project. If you're interested, this is in Cambridge. Everyone is welcome to visit because we are really looking for new collaborators to scale up. So this is about AI for building control we collaborate for 10 years already, including retrofit the entire house. So it has the IoT, all the devices, more than 200 sensors, just 2-floor buildings. We start, and the goal is not just thermal comfort. So we actually took, the HVAC is almost not functioning, like we want to do passive control, had the ventilation, everything there. So it's like, I didn't have the result. I want to show like this one, this is the outcome from our controller. The control we had is, because the representation work is recent work, so for this control algorithm, we already test for 2 years. It's actually more like MPC type of algorithm. But one big question, again, what's really the model to predict the air flow, or the model to predict the thermal? There's a lot of like delay in the system. We actually spend a lot of time to figure out what's the representation for the dynamics. Eventually, we did the LSTM, do the example. We had a 2 model. One do the long-term prediction, one model in the short-term prediction, and then put it into the MPC, but the model is very difficult to solve, which again, using some Bayesian optimization to find the control policy. So if you're interested, this is a real lab. Everyone welcome to visit. And another one is kind of my journey starting with the robotics, is the ultrasound machine. We had a manipulator, this is in my lab, and the doctor come talk to me, he's a radiologist. Then I want to work on this. I said, what do you want to work? Beginning, I don't think it's a hard control question, because the manipulator, right, if you want to go there, you can go there. So once I started working on it, I found the difficulties is. So this is a use case. You have a patient something going on, and then had a CT image, let's say, unfortunately had a tumor. So then the follow-up, probably every month, you can do some ultrasound scanning to see whether anything changes. So we actually will need using some other thing I will show for the next slide. So we'll see why we actually need some baseline, this ultrasound image. And then if something goes wrong, send to the doctor and probably do some other follow-up. So the challenge, when I start working on it, I realized it's much more difficult than the representation, just like of drone, have the motion capture. No, like it's the ultrasound, all the things that come from the ultrasound image. It is perception-based control, but I don't understand the image. I look at ultrasound, I have no idea what it means. There's no map. Everyone's like abdomen is actually different. So we need to do real-time biomedical image processing, because I need using this image to guide me. And the biomedical image processing, I don't know how many of you working on it. I talked with a robotics professor initially. He worked on the ultrasound before. He told me not going to work on it now. Like the quality of the image is really, really bad. Don't do it. But since I have like collaborator, let's go ahead to try. And then also safety. So eventually, let me show you, like we actually got very nice result, but after 3-4 years. So we first figure out the initial contact. If a patient lie there, where are you going to start? A lot of discussion with the radiologist. And then once we're getting our starting point, how to solve the mapping problem. Very similar to the slime in the robotics community. Find the landmarker. The landmarker will form the physiology. So we pick one landmarker. This is actually called, it's a big vessel, hepatic vein. So we try to find that part. And how to find it is trying to find some feature of it. Based on the 2D image from ultrasound, that's why I said it's good to have some 3D image as CT. As a baseline, I can do some mapping. Do the 3D restoration, this one using the UNet to guide it. Once we have the map, then go ahead to find the target location. And a lot of like finer tuning, actually local reinforcement learning algorithm been doing, because you go there, you think it's there, probably it's not. It's also based on the angle, like which the pressure you're going to use. So those to fine tune those pressure and the angle were depending on, like we had those our algorithm to fine tune it, and eventually getting the US image. So, and this is what you can, I said like, I don't know what the ultrasound image initially to find the target to go. I think my student took a Rust class and did something, and thank you for your feedback to the student. Right, so this is the ultrasound image, right? I had no idea what really I'm saying for the ultrasound image. We try to find the blood vessel, we find it, and getting more images than to construct the entire map. So once we collect, based on the CT image, we do the 3D HV construction. You can see that you can map very well. We have the map, that's the target, and then translate from the 3D image to the 2D image to see what exactly we're going to look for. It's a lot of like communication between the radiology like department trying to learn, and they also try to learn our language was really the bottleneck.